The inverse functions sine and cosine are opposite to sine and cosine. They are reflections across the line y equals x, and their input and output reflects that. The ordinary domain and ranges of cosine and sine are swapped for inverse cosine and sine. They can be interpreted geometrically by using the unit circle and by checking the angles that are outputted. Solve this trigonometric equation. First, you need to move the 1 to the other side, then divide both sides by 2. Since we have sine isolated and 1/2 on the other side, we can determine that the angle is either pi over 6 or 5 pi over 6. Step 4, we divide both sides by 3 for each solution. For step 5, we set k to different integers and check if they're greater than or less than 2 pi. These are my solutions. For the second equation, the first step is to factor the equation. This is with tan angle plus 1 multiplied by tan angle minus 2 equals 0. Since one of them has to equal 0, we test both sides to see the possible solutions. The first possible solution is tan equals -1, which can only happen if it's square root 2 over 2, and one of them is negative, which is negative pi over 4. It can only be on the right side of the unit circle, so that's why. The second possible solution is tan angle equals 2. 2 does not have a special angle, but it's still defined on the domain because it is not pi over 2 or odd multiple of that. Therefore, we gotta use the inverse. We use tan inverse 2 to represent the angle. The third problem, we use the quadratic formula to simplify it down, which gives us two possible solutions. Cosine 1 half equals pi over 3, and cosine 1 half equals 5 pi over 3. These are both possible solutions that are defined, so the second equation, we use the identity cosine squared equals negative sine squared plus 1 to eliminate the cosine to make it easier. Second step, we distribute the 2. The third step, we move all the terms to the left side. For the fourth step, we use the quadratic formula again. This leaves us with sine angle equals 1 plus or minus 3 divided by negative 4. Step, we test out the possible solutions by checking their sine values. Which is sine something equals -1, which could only possibly be 3 pi over 2. Second one is sine angle equals 1/2, which could be either pi over 6 or 5 pi over 6. So the solutions are these. Sketching these polar graphs. These ones I look for the radius and the angle, and I put the dots where they're supposed to be. I also used this other angle of pi over 6 to be more precise. In this picture, you can see the 5 dots that I put show the shape of the heart shape, where the goes at. Same with this one, except these angles down here made the shape. These ones inside were they had negative radius, so they went inwards, which is how I knew there was a loop. This one looks like a normal circle, so the balls don't really matter that much here, but they still I confirmed that it's like a circle. We have the complex number plane. The z right here is the normal one. By multiplying by 2, you scale it up by 2 in this direction. By multiplying by -1, you reflect across the origin and put it same distance, just on the other side. For if you multiply by 1/2, you just shrink it by 1/2. These are the radius. These are all of the moduluses. These are the arguments. This one, same situation, multiply by 2, scales up, divide by 1/2, divide by 2, scales down. Multiply by negative, it goes across the origin again, exactly the other side. These are my moduluses here. This is the arguments here. And for 6, we have the systems of equations. These are pretty easy. First up, you subtract R1 from R2 to get rid of this X right here. Set the new R2 to this. Second step, we get rid of the we want to get rid of the 3x and the R3, so we multiply R1 by 3 to subtract that. We set this to R3 again. Step 3, we want to get rid of the 8y, the y in R3, so we just subtract 2 times R2. Fourth step, oh wait, since we have that variable all alone, just fourth step, we gotta solve it. So we just divide both sides by -6, we get z equals 4. We solve R2 by doing that, by inserting z, get y equals 7, then we insert it, so z and y back into R1, we solve that and get x. And yeah, that's how you get the solution to this. For the next one, we subtract 3 times R1 from R3. Get a new R2, or a new R3, we replace that. We want to get rid of that X and and R2, so we subtract 2 times R1, place that, then we, to get rid of the Y in R3, we subtract R2. But it ends up being 0 equals -2, which is not true, so it has no solutions. Because no solutions would ever be true. It's different from the other one that actually had a solution for like real numbers because they work out.